Inside an industrial mixer, blades tear through a viscous liquid, folding layers of pigment over and over in an attempt to reach total uniformity. But look closer. Even under this violent agitation, specific clumps of color remain isolated. They cycle through the turbulence perfectly intact, refusing to blend with the rest of the mixture. Most of us assume that if you add enough energy and agitation to a system, the motion will eventually become random and the blend will become perfect. This resistance to blending reveals a structural battle occurring at the system's foundation. These stubborn lumps are the physical footprints of a specific mathematical phenomenon that prevents universal chaos. To understand why they survive, we have to look at the geometry of the flow itself, a geometry that makes perfect, all-encompassing chaos physically impossible to achieve.
In the mid-20th century, Andrei Kolmogorov, Vladimir Arnold, and Jürgen Moser studied what happens when a predictable system experiences a small disturbance. Their work, now known as KAM Theory, provides the blueprint for these stable pockets. They proved that small perturbations do not always shatter a system's underlying structure. Instead, many specific paths, or orbits, remain perfectly preserved, even when the rest of the system begins to drift. These preserved regions take the form of KAM tori. A torus is a donut-shaped trajectory within the liquid, an isolating boundary. Particles inside cycle endlessly and predictably along its surface, locked in a loop, shielded from surrounding turbulence. These tori act as unbreakable geometric barriers. They prove, even in the middle of disruption, nature is mathematically built to preserve pockets of absolute stability. While the tories stay calm, the surrounding fluid is governed by a different force, partial hyperbolicity. Partial hyperbolicity is a condition where a system possesses a mix of stable, neutral, and highly chaotic directions of movement. This diagram shows the mechanics of that space. Red arrows indicate stretching, blue arrows show compression, and a gray axis represents a neutral path that neither stretches nor shrinks. If that neutral direction doesn't push or pull, it theoretically slows mixing, but dominated splitting overcomes this. The red arrow's expansion is so mathematically intense, it completely overwhelms the neutral gray axis, forcing almost every particle into chaotic flow. This leads to a state called stable ergodicity. Even if the system's parameters are slightly nudged, the chaotic nature holds strong, ensuring the vast majority of points get thoroughly scrambled. The global result is a forced compromise. Unstoppable, violent mixing dominates most of the space, but that flow is constantly forced to bend and warp around the immovable KAM tori. To classify a system containing both violent chaos and indestructible order, mathematicians rely on a framework called measure theory. Specifically, they use the SRB measure to track where typical points in a system land over time. The SRB measure is a mathematical tool that describes the distribution of orbits within a chaotic attractor. If a stable pocket is mathematically rare enough, it is defined as a set of measure 0. Because these pockets are so tiny compared to the rest of the space, the SRB measure treats them as negligible when describing the system's general behavior. When thousands of new points drop in, 99.9999% of them are sucked into the chaotic swirl. Because almost every typical point ends up in this turbulence, the system is officially classified as effectively mixing, despite the existence of the tiny, stable islands. These same mechanics dictate the large-scale structure of the cosmos. In a spiral galaxy, gravitational orbits are often half stable and half chaotic, which allows massive, defined spiral arms to maintain their shape while individual stars within them drift into a chaotic flow. This explains why that unmixed lump in the industrial mixer exists. It is a visible KAM torus, a geometric island of order surviving the entropic pull of the surrounding liquid. This constant interplay between indestructible loops and unstoppable expansion defines the structure of the physical world. It leaves us with a critical question. How does the underlying curvature of space itself create these powerful expansions? That leads us directly into the study of geodesic flows.